Hello everyone, my name is Ritesh Pandey and in this video, we'll talk about the heating effect on various hydroxy acids and amino acids. Naturally, the heating effect and the nature of product will depend upon the position of OH group or NH2 group, depending whether it's a alpha hydroxy or a beta hydroxy or a gamma hydroxy acid. Now, deliberately I choose to speak about both amino acids and hydroxy acids in the same video because almost every time the heating effect and the nature of the product is identical. It could be a small part of a long problem, or at times different exams there are questions framed where the heating effect of such compounds is going to be required. So I recommend you watch this video till the very end and note down everything. We'll definitely begin with the case of alpha hydroxy acid, and right away alpha hydroxy acid would mean OH group is next to COOH group. So this is how an alpha hydroxy acid will be represented. Alpha means if this is COOH, the next carbon is alpha. So this is alpha hydroxy acid. Similarly, alpha amino acid is represented by RCHCOOH, and at alpha position you will have a NH2 group. So this is the general representation of a alpha hydroxy acid or an alpha amino acid. Now 2 moles of alpha hydroxy acid or 2 moles of alpha amino acid, you will see very similar results. On heating would lose 2 moles of water, So 2 moles would lose 2 moles of water to produce what's called a cyclic ester, which is basically a diester, or a cyclic diamide. Cyclic diester or a cyclic diamide. We'll see in both the cases the product is going to be very similar. Loss of 2 moles of water producing a diester or a diamide, cyclic diamide. And let's quickly see an example. Suppose for alpha hydroxy acid, a very popular compound, I take lactic acid, CS3CHOHCOOH. Now there is a particular way in which you will want to write the alpha hydroxy acid. 1 mole in this way and the other mole in this way. It will help you in recalling the product. So यहाँ पे OH ऊपर, COH नीचे, and the reverse for this one. Now naturally this is the very popular lactic acid. Now lactic acid, alpha hydroxy acid, I have taken 2 moles. Now remove water in this way, from this point and again from this point. Now when you remove 2 moles of water, the product formed will look like CH3CH, O, C double bond O, then a CH3 here, then O, a C double bond O, and C double bond O here, and C double bond O here will mean it's a cyclic ester out here, a cyclic ester out here, and naturally I'll want to call it a diester. The reason behind the formation of diester could be the stability of the 6-membered ring. We'll want to assign some logic behind the nature of the heating effect product. Similarly, for a alpha amino acid, I'll choose a popular compound. Suppose this time we take alpha amino acid. This time I take CS3CHNH2COOH, and again I want to write the other mole in this particular way. I want to write NH2 here and COOH above. When I do it this way, alpha amino acid, and I remove 2 moles of water in a particular manner. I remove water from here and I remove water from here. Now when I remove OH and hydrogen from this end and OH and hydrogen from this end, naturally the product formed will look like CH3CH. Now you will have a NH. O ki jagah you will have an NH, C double bond O, again a CH, CH3 NH here, and then C double bond OCH. So C double bond ONH, C double bond ONH, you have an amide there, you have an amide here. Naturally, I want to know it as a diamide. This is a cyclic diamide, like this was a cyclic diester. Here again, it's the stability of the 6-membered ring is why 2 moles of alpha hydroxy acid on heating would lose 2 moles of water. 2 moles would couple together to form a cyclic diamide or a cyclic diester. So you would have noticed the changes are exactly the same. The nature of the product is very similar. For an alpha hydroxy acid, it's a cyclic diester. For the corresponding amino acid, it's the cyclic diamide. We'll want to move to beta hydroxy acids and amino acids now. So when I call it a beta amino acid, naturally this time, or a beta hydroxy acid, I'll talk about hydroxy first. When I call it a beta hydroxy acid, this time OH is at beta position. Alpha, beta, gamma, delta is the natural sequence. So this would look like RCH CH2COOH. So if this is alpha, this is beta, this is alpha, this is beta, and you have a OH here. Naturally, this is how a beta hydroxy, alpha beta hydroxy acid will look like. When I talk about a beta amino acid will be represented like R. You have a NH2 at the beta position. Naturally, the sequence is alpha, beta, gamma, delta. This happens to be the alpha position. This happens to be the beta position. So this is the representation of beta amino acid. This is a beta hydroxy acid. You will see in both the cases the product will be very similar. On heating this, just remove a mole of water. Dehydration here. Now when you remove a mole of water, dehydration of an alcohol kind of thing, you get a very popular structure. It's RCH double bond CH COOH. Now naturally you will find this pi bond in conjugation with this double bond. This is conjugated, this is in resonance, double single double, this is conjugated, this is in resonance, and I'll want to call it an alpha beta, unsaturated acid. Such compounds are going to be stable because of resonance, double single double, loss of water, you get an alpha beta unsaturated acid. You might see something similar with beta amino acid. Now beta amino acid would rather lose ammonia. Suppose it loses ammonia, deamination, यहाँ पे dehydration, यहाँ पे deamination है, and if you remove ammonia in this way, see the nature of the product will be identical. Here you will get RCH double bond CH-COOH, and here again it's alpha beta unsaturated, double single double, it will resonate. So here again you have an alpha beta unsaturated acid. See, the nature of the product is same. The effect of heating is the same. This loses water, it loses ammonia, and both of them produce alpha beta unsaturated acid. Naturally, the logic behind the formation of such compound would be double single double, which is resonance. After beta, we can move to gamma amino acid and gamma hydroxy acid. So gamma hydroxy acid, and now I can draw a structure like COOH here, and this will be alpha beta gamma, OH here, and this might represent alpha beta gamma. It is a gamma hydroxy acid. Similarly, a gamma amino acid, and I'll want to draw a chain where alpha beta gamma, you'll have a NH2 group here, and NH2 is at gamma position, so it's gamma amino acid. Now when it's a gamma hydroxy acid or gamma amino acid, the length of the chain is big enough, to undergo intramolecular dehydration. Intramolecular dehydration, you know about acid alcohol forming ester. Acid alcohol forming ester. Acid alcohol forming ester, remove water in this way, remove water in this way. Remove water in this way, intramolecular esterification, loss of water, and the reason would be the chain is big enough to form a stable ring. See, it will give you a 5-membered ring. I think it will give you a 5-membered ring. You will want to count like 1, 2, 3, 4, and the 5th would be oxygen. It will be a heterocyclic ring, and something very similar will happen here. Something very similar will happen here. If you remove water like this, if you remove water like this, and count like 1, 2, 3, 4, 5. Here also you will get a 5-membered ring. Intramolecular dehydration in both the cases. Intramolecular dehydration in both the cases is the heating effect, and naturally the product will look like a ring, a cyclic ester, which is called a lactone. So let me draw a 5-membered cyclic ester. Which will look like a 5-membered cyclic ester would look like this. You know, I'll want to again give the counting 1, 2, 3, 4, and this is 5. Now, 5-membered cyclic esters are called lactones. Cyclic esters are called lactones. In this case, you can call it butyrolactone. You can call it butyrolactone. You can also call it gamma butyrolactone because it comes from a gamma hydroxy acid. Again, butyro because it's a 4-carbon compound eventually. So gamma butyrolactone, this is how the final product will be obtained. For gamma amino acid, you lose water in this way, Again, you will get 1, 2, 3, 4, 5-membered cyclic amide. You will get 5-membered cyclic amide. If this is how you draw the 5-membered cyclic amide. Now, cyclic amides are called lactams. And you might want to call it gamma butyrolactam. Naturally, intramolecular dehydration producing intramolecular ester, cyclic ester or cyclic amide, which are called lactones or lactams respectively, because a 5-membered ring is stable, and after gamma will move to delta. And I think most of you would have understood, in delta same thing will happen, because in delta you will get a more stable 6-membered ring. So delta hydroxy acid, which will look like a OH here, alpha, beta, gamma, delta, you know, is the natural sequence, alpha, beta, gamma, delta, and certainly it will give you a more stable, 6-membered ring, delta amino acid will look like NH2 here at delta position, and naturally alpha, beta, gamma, delta. You will want something very similar to happen here again, because if it's happening in the same manner like before, which is intramolecular dehydration, this time you will get an even stable 6-membered ring. Naturally, it will be oxygen or nitrogen in the ring, and the product will look like a 6-membered cyclic ester. It will look like a 6-membered cyclic ester. 6-membered compound is even more stable. Let me call this lactone. Which is very popular. It's called a valerolactone. 5-carbon acid is called valeric acid. So it's a valerolactone. You can also call it delta valerolactone. The corresponding amide 6-membered would look like this. 6-membered is even more stable. And the lactam this time, intramolecular amide, lactam this time could be called valorolactam and a delta valorolactam. Now it's happening exactly like the previous case. You know, something very similar was happening with gamma hydroxy, which was giving you a 5-membered ester or a 5-membered cyclic amide. It will happen even better in the delta wala case, because a 6-membered ring is even more stable. this happening for even the next carbon. Also alpha, beta, gamma, delta will do, but suppose you are given a case where they are further apart, which is epsa, and that will be the last case we'll be discussing. So if they are further apart, if it's epsa hydroxy acid, where 1, 2, 3, 4, 5, you have alpha, beta, gamma, delta, epsa, and OH here. Now this time a similar dehydration will give you a 7-membered ring. It will give you a 7-membered ring. 7-membered ring is not that stable. Naturally 7-membered ring is not that stable. I could very well draw a 7-membered lactone which will look like but 7-membered ring is not as stable as a 6-membered ring. The order of stability is 6-membered is most stable, followed by 5-membered. 7-membered is also stable but not that stable. You might call it a lactone which is a caprolactone बोलते हैं, epsa caprolactone, because the corresponding acid is called caproic acid. Common name is caproic acid. And something similar happening in amino acid. See, this is alpha, beta, gamma, delta, and epsa would give you a 7-membered lactam. So this is a 7-membered lactam. This is a 7-membered lactam, which I told you could be called a caprolactam. Or an epsa caprolactam. Lactone, lactam, 7-membered. Now 7-membered is not very stable. So either this will be the result, or when the chain is this big or the two groups are this apart, it can start undergoing intermolecular dehydration. So this is one possibility. Naturally another possibility is if it's happening intermolecularly. Intermolecular का मतलब हो गया, you have a COOH here or OH here, so I can write a OH here, and suppose this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So there are 5 CH2 units, then a COOH. I'll take another molecule OH, then 5 CH2 units and COOH. Then I can take another OH, 5 CH2 units and COH, and so and so. And if I remove water intermolecularly, this was intramolecular, if I remove water intermolecularly. Now when I remove water intermolecularly, say water in this way, then water lost in this way, then several moles of water gone, this will form a polymer, You would have heard the name polyester before. This is going to be a polymer. This will carry on, and this will become, or this will be called a polyester. Naturally it's called polyester, which we start calling polyester in simple language. The same happening with amide. You can figure out, can give you what's called polyamide. So this is the corresponding polymer. If it's epsa amino acid, you will want to call it a polyamide. So you might have polyamide formed, polyester formed. It will depend upon the choices, the options which are given to you in the exam. But as I told you, this is a possibility. As they keep on getting further apart, if they're even more apart, if OH, COH or NH2 COH are even more apart, then it will start forming the long chains only. Polymer formation would be more feasible. Ring formation will stop, ring formation nahi hoga. But this is what we had to learn prima facie. Epsa 7-membered ring, delta 6-membered ring, gamma 5-membered ring. We are happy with 5-membered ring, cyclic ester, cyclic amide. Now beta is a different case, dehydration, deamination, and you would know about the stability of such compounds. Resonance hota hai, alpha beta unsaturated acid, and certainly for alpha hydroxy acid, we wanted 2 moles to lose 2 moles of water to form cyclic diester or cyclic diamide. Yet again, the reason of the formation of cyclic diester or cyclic diamide could well be the stability of 6-membered ring. I hope this video is going to help you in all questions based on the heating effect of hydroxy acids and amino acids. This topic is certainly there in the chapter amino acids. Organic chemistry, towards the end of the textbook, amino acids, you are supposed to learn about the heating effect of different amino acids. So heating effect of amino acids is already covered in this particular class. I wanted to talk about hydroxy acids in the same video for the reason I told you, and I hope this is going to help you in the real exam. This much for the time being. Thank you so much.